All right, well, this is week 8, and we're going to continue talking about sequencing in SuperCollider. So last week we talked about routines and clocks and quantization, and that's one of the main options that you have at your disposal for doing sequencing. And today we're going to talk about a different branch of sequencing tools, which encompasses 3 broad categories of classes, which are patterns, events, and streams. And in the, I think, where is this again? If you're in the help browser, you can go down to a category called streams, patterns, events. And this contains a bunch of help files mostly, but then there are also some guides and tutorials. In particular, this practical guide is something which I recommend to people quite often as a way of understanding patterns and events and streams and their relationships to each other. So we've already seen a little bit of streams when we talked about routine last week. A routine is actually a type of stream. Its grandparent class is stream. And there are other types of streams than routine. But in short, a stream is some process or object which represents a sequence of values and which responds to the message next by returning to the user the next value. So we'll see streams again in this context. But let's talk about some new stuff first. So we'll start by talking about patterns. So in SuperCollider, there's a large library of objects which are collectively called patterns, and one of the best descriptors of this family of classes that I've seen is referring to them as a concise score language. A concise score language meaning classes which give you the ability to efficiently and with a minimal amount of text represent various sequences of all different kinds. And I just want to reiterate a distinction we made last week, which is the distinction between objects that define sequences and objects that perform sequences. So patterns are the former. They are a score language. So they define a sequence, or they can be used in combination to define some complicated sequence, but they don't actually perform it, and they aren't the object that actually does the work of delivering the values to the user or whatever needs the values. So patterns, it's, you can grab my notes here just so I don't accidentally overlook something. And all right, so there are lots of types of patterns. And like learning a language or like learning a programming language, you don't need to know every single one in order to use them. Again, it's just a matter of getting familiar with a core group of commonly used patterns, and that will give you a good vocabulary for expressing sequences. So on the course website, there is a document you can download called Common Patterns. So this is probably what I would recommend first. Instead of just me spending 15 or 20 minutes demonstrating all these different patterns, I've given you, one example of each of these common patterns, and I'll just go through a couple of these very quickly. They all start with a capital P. This is kind of the, it's just because something starts with a capital P doesn't mean it's a pattern, but all pattern classes start with a capital P. So Pseq, which is short for sequence or sequential, represents an object that defines a sequence, an ordered sequence of things. And there are 2 arguments that Pseq takes. The first is called list. This is just an array of things. They can be numbers. They don't have to be. The second is the number of times to output that sequence. And so right now it's inf. So we define a pattern P, and then we create a stream from that pattern and store that in a queue. Again, keeping distinct these 2 ideas of representing a sequence, defining a sequence and performing a sequence. We can, we've already seen next, right? So if I just call next repeatedly on Q, it will return the values that the pattern P defines, which in this case is going to be 4, 9, 3, 4, 9, 3, 4, 9, 3, and anything, right? Forever and ever and ever, because the repeats is inf. Something I didn't show you last week was an alternative method, next n, with a capital N, and this returns an array of n next values, in this case 20. So this is just, if you want to just grab, a chunk of values, instead of having to like take them one by one and manually load them into some collection, you can just, get as many as you want on demand. Right, and you can see that, Pseq, is when it's converted to a stream is a special type of process that knows where it left off after each next. So the last thing we output was a 4. So if we next n 20, the first thing is a 9, right? So it picks up exactly where it left off. Prand, as the name suggests, it just randomly picks an item from its collection. So here's the array from next n 20, and as you can see, each one is just randomly chosen from these 3 values. It's just each one is equally likely to be chosen. Pxrand does the same thing, but will never pick the same item twice in a row. Pwrand picks randomly based on a second array of weights. In this case, here are the normalized percentages, so it's most likely to pick the third item. Next is the second item, and the least likely item to get picked is the first one. So we'll see 4, maybe not at all. Though we saw 1 4 there. But anyway. So you can go through and look at all these patterns. A lot of them are very simple in terms of how they behave. Then we get to a few more interesting ones. These are sort of, I sometimes call these choose your own adventure patterns, pfunc, plazy. It's like a define it yourself kind of thing. Pop into the help files to see more examples for each one of these. And I'll sort of stop it there. You can also, there's parts throughout tutorials 10 and 29 on YouTube, which also introduce various patterns and talk about how they behave. So most of these patterns, not all of them, but many of them are what we might call value patterns. And some of them are strictly numerical, but really all of them, maybe with a few exceptions, are value patterns in that they return, when each pattern is converted to a stream and nexted, it returns a sequence of values. Might be numbers, might not be. Pseries, for example, is always numerical. It's an arithmetic series. So we start here, we add this value repeatedly, and we do it this many times. So we'll get 1, 3, 5, 7, 9. We start at 1, we just add 2, add 2, add 2. So there's no way to get something out of Pseries that isn't numbers, right? It's inherently numerical. Pseq, on the other hand, you can put whatever I recently changed SuperCollider so that it automatically adds like when I do a parenthesis, it automatically adds the other one. And I go back and forth between this, so I might mistype some things here. But if we just change this so that it's defines a sequence of 4 high 3, so number, string, number, number, string, has no problem with this. So Pseq doesn't have to be numbers. Some of these do, some of these don't. But I think it's safe to say that all of these are what we call value patterns. So they don't necessarily interact with sound. They don't produce sound. They just give us values. So it's basically an alternative to some of the, like, you might remember this from last week. We made this this routine from a function which starts at -12 and returns that, and then repeatedly 3 times in a row we'll add either 2, 5, or 7, and so it gives us this kind of random note generator. And this is kind of a, relatively speaking, a lot more to have to think about and have to type, and patterns can very often condense this kind of job into just 1 or 2 lines. So these value patterns are prepackaged units that perform a specific task so that we don't have to write it ourselves every time. It's very, very useful in that sense. Here's a somewhat simpler example that I made. I think this is from the book, actually. So here we're doing the same thing, defining a function and creating a routine from that function. And I'll just walk you through it. We're using a while loop. So while is another type of conditional operation, like if. If checks some condition, and if it's true, then it does something. If not, it does something else. While is kind of similar to loop, which we saw earlier. Loop just does its function forever, unconditionally. While checks a condition, and if it's true, it performs this function, and it just will do this forever. It will perform its function if this is true, then it checks it again. If it's still true, it performs it again. Still true, performs it again. So what we have here is an incremental counter, which starts at 0, and the check is it less than 6? And we just want to do this 6 times. And so what we do, if it's true, if we're not at 6 times yet, we return the number, which happens to start at 50, and we add 7 to that number. And then we increment the counter. And then we check again. Oh, it's still true, because 1 is less than 6. So then we yield 57. And then we add 7 again, and then we increment the counter. So this little function will define a routine on which we can call next. And we get 50, 57, 64, 71, 78, 85, and that's the end. Because at that point, we have exited the while loop, and we're at the end of the routine, and so there's nothing left to return. There are no more yields. So let me just very briefly show you how you can transform this into do the same thing with patterns. So this is an arithmetic series. We start at some number, and we incrementally add some value. So what we can say is pat equals Pseries, start at 50, add 7, go forever, Pseq equals pat.asStream, and we're done. Now we can say Pseq.next. Oh, it should have been inf, should have been 6. Yes, should be 6 if we're doing the exact same thing.
Oh, wow.
Yeah, so when you're doing some sequential numerical operation, very often it can be reduced to just 1 or 2 patterns, and it's very convenient because it saves us a lot of time. One thing that's really quite nice, let me actually move this into my actual lecture code here. One thing that's really nice about patterns, these value patterns, is that they can be, you can perform, if all the patterns involved just are numerical in nature, you can do math with them as if they were numbers. Let me give you an example. So let's say pat equals Pseq 1, 2, 3 forever. And we can say pat equals pat plus Pseq 10, 20 forever. All right? So we define some sequence which goes 1, 2, 3, 1, 2, 3, 1, 2, 3, and we add it to a sequence which goes 10, 20, 10, 20, 10, 20 forever. And we add these 2 patterns together. And it's quite similar to the way array addition works, or math with arrays works, which is that we perform the operation with corresponding pairs. So we get 1 plus 10, then 2 plus 20, and then 3 plus, oh, whoops, we don't have anything. We will just go back to the beginning, right? So that's what's going to happen here. We get 11, then 22, then 13, and then, so each pattern just goes through its sequence independently, and each one of those pairs gets added together. So we can just, because this one has 3 and this one has 2, they will, basically the total sequence ends up being 6 values, right? We have 11, 22, 13, 21, 12, 23, and that repeats. So you can, if it makes sense to do this operation with the individual items that the pattern produces, then you can do this operation with the patterns themselves. So multiplication, addition, raising something to the power of, rounding, all of that is fair game. And so this is I would call this like math operations with patterns. You can also nest patterns. which means put a pattern inside of another pattern. An example of that might look like this. We'll space this out on a couple lines here. So we'll say first output 5, then output a random number between 1 and 9. So the arguments here are minimum, maximum, number of times to do it. This is the same white that we see in white noise, where it's just complete uniform randomness. And then we'll output 6, or no, let's do 12, and then we'll say Pseq 2, 3. We'll do that twice. And we're going to do this whole sequence 3 times. So just this is like, I would call this a composite sequence, or a composite pattern, a pattern which is composed of multiple patterns working together to create some specific sequence that we can't really do with just one pattern. All right, so first we're going to see what comes first. Right, 5. And then what comes after 5?
Well, what comes next is random, no?
Yeah, it's random. It happens to be a 6, okay? And then we see yeah. Well, this pattern has a length of 1, and that was its output.
Ah, no, that is the next one.
Right, so now we'll get to 12. And then what do we expect to see?
We will see then 14.
No, 2, 3, 2, 3.
Ah, those two. Oh, yeah, you already finished with that, so now it's doing yours.
Yeah.
Okay.
And then what do we see?
3.
No, not 3. This is the number of times.
Now we
For
go back to 5.
Right, we go back to 5. 5, random, pick 5.
And now
12, 2, 3, 2, 3. And then 5, random, pick 5 again. 12, 2, 3, 2, 3. And then we are done. Yeah. All right, so that's composite patterns or nesting patterns or whatever. So that's definitely take a look at the common patterns and give it a try. There's some examples in the book too. For example, here one example in the book is if you are using patterns to generate stereophonic pan positions. So like -1 is left, +1 is right, 0 is center. And if you want the pan positions to be random, but go left, right, left, right, left, right, you can do this in a couple of different ways using patterns. One way is to, actually this might be a good exercise. Can you come up with a, I don't know, we're just introducing these, so it might be kind of a tall order, but how would you, you don't have to give me the exact code, but how would, generally speaking, what would be your approach if you wanted to make a pattern that outputs random numbers between -1 and +1, but so that the sign always switches, negative, positive, negative, positive. So.
Let's see. Always switches.
Yeah.
Okay, can we use Pseq first?
Sure. Let's start with a Pseq.
Yeah. And it's going to be a list of -1 and 1.
Okay. Good. How should we say? We'll just do this. We'll just imagine an infinite sequence.
Yeah.
It's
But
okay.
we need to nest something in there, right?
Yeah. So this just we'll do it as we go. But so right now we're just going to get.
Exactly. But we want to randomize.
Yeah, we want to get a random value. So basically the first value will be a random value between -1 and 0. And the next one will be a random value between 0 and 1. Right? So that's I'm just conceptualizing what we want to do here. Rand. Yeah. So if we did something like this, right? Right? Because this expression is going to give us a random number between. Maybe we should do between 0 and 1, right? Right. So this is just giving us a random number, and if we multiply it by this pattern, right, then this is going to be this number times -1, and then this number times +1. There is a problem, though, and I'll show you. We'll see what we get when we do this. So this is a common thing I see. It's just you're working with patterns, and if you stick a non-pattern language side expression in here, this will not automatically patternify itself. It doesn't say, oh, I should just do myself, multiple times, right? No. When you evaluate this code, this expression becomes whatever it becomes, and you might as well have typed, this. And so then we're just multiplying this number. It was initially chosen randomly, but it will not repeatedly make random choices.
Can we use like Prand?
Prand, what would we put in the Prand? It takes an array and chooses randomly from that array.
Which is something that we're doing.
Yeah, I mean, we can't provide an array of every single number between 0 and 1. So Prand is good when we have a collection we're choosing from, like picking marbles out of a bag or something. But there's another pattern, which is actually on the screen right now, that is a better choice. It is Pwhite.
Oh, yeah, it is. Because it gives you a low number and a high number.
Right, and so this pattern, we're doing the same thing that we did kind of up here. We take this pattern, which just toggles back and forth to determine the sign multiplier, and this one, which is just picking unipolar values between 0 and 1. So now we will get, see how that negative sign?
So it's between live, but randomized.
Yeah, but randomized on each side. So this will give us kind of, if we use these as pan arguments in a stereo synth, then each synth will be left, right, but not always the same distance from the center. Yeah. So these are the kinds of things that I hope that you will get comfortable with, and sort of thinking with how to make your numbers do what you want them to do by expressing the sequences with patterns. So it takes a little time to get used to it, but that's an introduction to value patterns. Value patterns. Value patterns up here. So now I would like to talk about events. So we're going to switch gears, and so we're talking about value patterns, now we'll talk about events, and then we'll bring those together, and it's going to seem like we're doing a hard left turn here. We're like leaving the world of sequencing momentarily, because an event is really just a type of collection, similar but different from array. So an event has a direct syntactical representation which is enclosed in parentheses, and instead of an ordered collection like an array, it's an unordered collection where each item is stored at a key represented by a symbol. I'm just using these silly alphabetical keys, but you can call these whatever you want. So this E, we've stored in the interpreter variable E something which is in fact an event. And we can say keys to see what keys are available, and we can access the value stored at a key by using this square bracket syntax. So E at the symbol ABC returns the corresponding value stored there. So E at DEF returns 7. Right? And I think there's an alternative syntax. You can actually do this with events. As long as your symbols start with a lowercase letter, I think this is valid. And what's one feature of events is that they there can only be one. Each symbol is unique. So if we say I would like ABC to be the number 12, it does not add a second ABC symbol. If you look at the event in the post window here, it has overwritten the value that was previously stored at ABC with the new value. So there cannot be any duplicate symbols here. So this is the event as a storage mechanism. It is useful. I like sometimes using it to store buffers. In fact, the code at the end of chapter 4 that loads, or one of the companion codes in chapter 4 that loads files into buffers, stores them in an event. And there's other reasons you might want to use an event. Anytime you need something where the order doesn't really matter and you want to name, provide a sort of a name tag which everything's stored in it. It's all very useful. But in the context of pattern streams events, the event also models an action to be taken in response to the message play. So you can play an event. So I'm going to boot the server, and the event, what you might call the event infrastructure, all of the code under the hood that makes events respond to the play message, is so thorough and detailed that you can actually play an empty event. And you hear a little sound. Right? So there are so many things happening here because we have not created a synth def. We are not creating a synth. We haven't specified any parameters. And we see all of this, stuff in the post window. A frequency. This is middle C. Where did that come from? It has an amplitude. So there's all of this infrastructure in the background, which has been made for us to simplify the process of making sound. Yeah, this is like the default. It's called the default note event. So this there are many types of actions modeled by events, and I think we can see them all by doing event.eventtypes.keys. Yeah, and so here is the complete list of all of the keys that represent types of events. I have never used almost all of these. A lot of these I'm not even sure what they do. I can only guess from how they're named, but note event. This is the default type of event if you don't specify a different type of event. There is also the rest event, which, as the name suggests, it doesn't do anything. It represents a rest. So it just, and there's maybe a couple other I've used, but I think even as you progress from beginner SuperCollider user to intermediate SuperCollider user, you may find yourself using the note event 99.9% of the time, because this is the event which models the action of creating a synth from a synth def. That's what the note event is. One or more synths. It's just so let's unpack the note event a little bit more. I'm going to there's a bunch of parameters which are in the note event, like amplitude. So the default is 0.1, but we can change this. Right? There's the default frequency, which was middle C, which is like this. But we can put whatever we want in here. Right? And there's also the type, and by default this is the note type event. If we make this a rest event, it won't do anything, right? Something which is another feature of the note event is that under the hood, there's a very substantial and detailed hierarchy for specifying pitch and loudness. So freak is an option, and we've seen that we can do something like MIDI CPS to convert a MIDI note number to cycles per second. So this is fine. We can still do this. But we can also do this. We can say, I don't want to converse in hertz. I want to converse in MIDI note numbers. And we could just do that directly. And the note event knows how to convert this, basically. Let's see, events. Let's see if I remember how to do this. Just give me a second to dig this up here. Yeah, just you're getting a glimpse at just how detailed all the stuff is under the. Okay. Okay, here's the code that calculates MIDI note, right? Actually, let's look at another one. Let's look at freak. Right? So here's the function which, on the back end, does the conversion. It takes whatever we provide for MIDI note, it adds this chromatic transposition value and multiplies it by a harmonic value. And whatever that comes out to be is what gets dumped into Freq. Right? So what we've done is we've provided our own MIDI note, and we're just letting the event structure use the default C transpose, which I happen to know is 0. I think we can even, let's see if we do it here. Yeah, it's 0, so we're adding nothing. And the default harmonic is 1, so we're multiplying by 1. So we put in 60, and that gets converted to cycles per second, right? And that's, so if we don't specify either MIDI note or frequency, we still get something, because MIDI note, here's its complicated function. It derives from something called note, which is this, which derives from degree, which starts at 0. So this is in the book, and I try to sort of unpack how this all works, but we can think in terms of degrees, like this. Right? Just you pick some scale, and we say just do the scale degrees in that scale. We can do note in this system. So degree is like modal stuff, like major, minor, chromatic, whatever. It's just a scale with degrees. Note is kind of like different ways of dividing the octave, with the different types of equal temperament and things. But 0, I think, is middle C. You can go this way. And then MIDI note, this is our good friend, MIDI note, if you've ever used a MIDI keyboard, where 60 is middle C. So many different ways of specifying pitch without us having to really do any work other than understand kind of the basics of what is available to us. Right? So here, we can also, like, just to show you the, let's go down to like 50, and we have our C transpose. We can, right? We're just chromatically transposing whatever our MIDI note is, and we can say harmonic 1. It's just a multiplier. The options are almost too plentiful. It becomes kind of this wild west of pitch. So there's also, and going back here to just amplitude for a second, we can do our usual 0 to 1 amplitude. If we want to think in terms of decibels, that is allowed. So right, so 0 being equivalent to an amplitude of 1, and then just decreasing as we go down to negative infinity or whatever. Let's see, if we go to the source code for event and search for synths, here we go. We have the default synths, and there it is. That's where the sound we're hearing is coming from. Because when you launch SuperCollider or boot the server, I forget exactly when this happens, but at some point, this synths gets added. And its name is default, and it is basically a couple of var saws. And let's see, this is the frequency, and then we have this. How does it work? It's going through a low-pass filter, and it's got some line controlling its cutoff. It's multiplied by an envelope, and it's panned. And so these parameters are fair game. We can pan the default synths. So if we go back here, we can say pan -1, +1. All right. Anyway, so this is the event. Let me just briefly show you how we can, use our own synths. So let's go back. Where am I? Oh yeah, I made this synths ahead of time. So I'm going to load in my PVC buffer, and I'll just very briefly. We have a play buff with some arguments. Basically, just playback rate, start position, whether we want to loop. I pass it through a resonant low-pass filter with arguments for the cutoff frequency and the reciprocal quality. I multiply it by a percussive envelope, and we pan it. So, it's, in many ways, it's a lot like the default synths. We have a source sound, it gets filtered, it gets panned, it's got an envelope, and that's all we get. So we can make a synth, like this. Like here's just the default sound. There it is. And then here it is with a some filtering. We can increase the quality. I'm getting a little bit more resonant. Rate. So we have all the usual controls. So if we want to use an event to play this, we make our event. And if we just do this, of course, we get the default synth def. So the key to specify which synth def to use is instrument. Play. Yeah. Yeah, so instruments is okay. I'm going to look for the synth def with this name.
So right now it's instrument default.
Right, if we say default, that's our default synth def. But now we're doing this. And I really should be specifying buff B. All right, now, something to observe here. If we do this versus this, it's right, yes, it's using the default amplitude of the default note event, which is 0.1. And how you know this, you might not know this. This is kind of the reason people who don't like the event paradigm, this is why they don't like it, because there's a lot of secret things happening under the hood, which are convenient sometimes, but inconvenient other times. So we can always override keys in the default event, right, as we like. We can also change the attack so it's a little softer. Right, so because I've got this attack parameter on my envelope here. So all of the arguments in the synth def, all of these things here are fair game, right? They will. Yeah, they're all fine, and so that's kind of the gist of it here. We just say play this synth def, and you funnel a bunch of extra arguments in for keys corresponding to either arguments defined in the synth def or keys which are inherently part of the default note event. So the part about the synth def arguments is pretty obvious, right? You declare your arguments, and then when you play an event, you can plug them in. But let me change this synth def a little bit, just to show you what I mean. And I'm just going to do a sawtooth wave here. Let's do 200. And I'm going to make this into an ADSR envelope. Okay, so it should be, I called it play, that's too bad. Okay, we'll do that. I'll run this again just in case I want to still use that one. So now I've changed the sound source, and I've changed the envelope so that it is a sustaining envelope. Right, so what that means, if we go back to our synth version, just make sure this isn't too loud. Okay, we can turn this up. I was just being safe. Right, sustaining envelope, so we have to actually set the gate to 0 in order to turn it off. Cue a little bit of event magic here. Actually, we just don't need the slash there. Okay, let me make the amplitude higher so you can hear that. It turns itself off. How did it do that? Right here, we're completely at the mercy of our ability to silence it. Right? We create a synth, it's on. There is no mechanism to automate the process of closing the gate on the envelope. But over here, it does it itself. Right? Yeah, sure.
Does it happen that an envelope is also included in the default event?
Not quite. No, you're not quite correct in that there is no, the event structure is not modifying our synth def or our signal algorithm in any way. But the note event includes a key called hasGate, and by default, it is true. If it's false, oh, wait a minute. Wait a minute. hasGate. Either I misnamed this. It might be sendGate. Yeah. Okay, send gate. I just had the wrong name. So I cannot stress this enough. I'll hit command period here. I can't stress this enough. The event infrastructure, even if we just limit our scope to the note event, is enormous. There's a lot of things going on which allow us to customize exactly how the synths are created. So one of those is the fact that when we play a note event, under the default conditions, a corresponding gate 0 message will automatically be sent sustain number of beats later. So if we say sustain 0.2, right? So we 0.2 beats, and I think we're operating on the default tempo clock here, so 0.2 seconds. After the note begins, a gate 0 message gets sent, which initiates the release. But if we set this to something like 3, yeah. So this is nice, right? Because we can, all of a sudden we can just play, use the events to play these synths, to create these synths. Even though they have sustaining envelopes, we don't have to worry about a bunch of stuck notes. We don't have to micromanage anymore. So that's very nice. And I think at this point, I'd like to return to our big discussion of pattern streams, events, and introduce a pattern which kind of brings it all together, and that is Pbind. Pbind is a pattern which defines a sequence of events. Compare that to all of these common patterns. These are patterns which define a sequence of values, usually numbers or just individual things, right? But not events. Pbind defines a sequence of events, and the structure looks like this. We provide inside of the Pbind comma-separated pairs of symbol value, just like we've been doing here. Symbol value, etc. So we'll say instrument saw, and it's a little bit like the syntax is a little bit different. I don't think we can do this anymore. With the this is when you put a name and then a colon, it turns green to show that it's a symbol. But we have to do it this way. There's a couple. We'll just get through this first, and then I'll talk about the syntax nuances. But we'll say amp 0.2 and freak. I don't know, 300, and sustain 0.2. Make this a little louder. Okay, so there we go. We've defined pat to be a Pbind, which defines a sequence of events. Now we're going to do this you pretty much never do this, but we're going to do this manually. We're going to turn this pattern into a stream, just like we've done before, and now we can call next on this Pbind, but the only thing is we need to provide an empty event as we call next, so that Pbind has a place to store the values. And then we can just play the event that comes out. Okay, pretty boring. But what's happening here is the Pbind, when it is asked to produce its next value, when it's transformed into a stream, and we call next, it's going to create an event, like we did up here, by binding values to keys. That's why it's called Pbind. So it's going to say, okay, we're going to have instrument, that's going to be saw. Then we're going to have amp, that's going to be 0.4. Then we're going to have frequency, that's going to be 300, and sustain, that's going to be 0.2. So it's just making these events. And all of the previous things are still fair game. We can do this. Right? You can think in terms of MIDI notes. You could think in terms of decibels. It's probably a very similar value, but you get the idea. And so this is like the manual version, but we don't have to do that. In fact, what we usually do is we don't next a Pbind, but we actually play a Pbind. And you might ask, okay, where does the timing information come from? There is yet another key in the default event infrastructure called dur. And this defines a duration in beats relative to the clock on which the pattern plays, which determines the timing distance between the onset of successive note events. So the default is 1 beat. So this will be exactly the same. And we can make this shorter. And you have to keep in mind what we're doing here is just, making multiple synths. Every time Pbind, as a stream produces another event and plays it, it drops a synth onto the server. Right? So we actually have a lot of different ones here. And okay, the final, I think, important thing is that all of these values can be value patterns, right? So we'll do Pwhite 40 to 80. You can nest, you can do whatever you want, as long as whatever you pair with a key, as long as it is some valid pattern that defines some valid output, then you're fine, right? So let's just make this a little quieter and okay. And we can say let's do Prand, we'll say 0.2, 0.4, 0.6. Just pick one of these random dur values. I always feel kind of bad because whenever I introduce this, my patterns just end up being the stupidest sounds. It's not exciting. There are so many subtle, crafty things you can do here. Like if we were to go back to, this synth. In fact, why don't we try that real quick? We have our play synth here, and let's crack open a quick Pbind. We'll try to do something sort of interesting. Yeah, so we got to say use play, and I'm going to try to do something with the filtering maybe. So I want the releases to be all really short. Something like this. We might as well specify the buffer while we're here. Let's see, this is still valid, good. All right, so this is just like kind of a starting point here. No, pat.play. We might even want to, I don't know, make a tempo clock running at 108 beats per minute. Okay, so there we go. And so now we can play this on clock T, just like we did with routines. And these dur values are going to be beats. So it's going to be a half beat at 108 beats per minute. Okay. Let's do, all right, so I'm going to do, for the duration, I want to do a really short duration, like 6 times. And then, okay, let me start again here.
So the duration is going to be a sequence.
Yeah, I want to do this duration 6 times and then a long duration. So we get like 6 rapid notes and then we wait, and then 6 rapid notes and then we wait. This Pseq is going to do this one first, and then we'll just say I think we could even just do like 2 or something, right? One reason this works is because every object can be interpreted as a stream, because next is defined for everything. If we say 0.2.next, right, it just returns itself. It's the same thing as like Pseq 0.2inf. So I think we can just put a number here, and if we want to be extra clear, we could do this. Right? Yeah, and we'll do this forever. Okay. So now that's a little too fast. Let's do a little too slow. right? And then what I wanted to do was like mess around with this filter value, because if we set it here, right, set it here. So I'm going to do pgeom, which is like Pseries, but it's a multiplicative thing. So we'll start at 20,000, and we'll just cut it in half. We'll do that also 6 times. And then oops. Yeah. And then we'll just copy this and make it like some, not actually sure where this ends up. So let's say as stream all, just to see what those numbers are. A little trick here. So 625. So then we'll do 625 divided by 2, whatever that happens to be. All right, and we better take this away. We don't want this there anymore. And do this forever. And this is where I check my work, make sure I didn't goof something up here. So we're going to make 6 notes, and then a 7th, and then there's going to be a longer wait after the 7th. So then we're going to start with a high cutoff frequency and ending down here. Let's see what happens. Yeah. Yeah, and then we could maybe take the rate so that it goes, copy this. I don't feel like typing all that again. So we want to start at 0, -1, 6 times, and then we'll do minus 1, 2, 3, 4, 5, 6, and then we want to do MIDI ratio, right? Because we're going to 0, -1, -2, -3, -4, -5. Oh, you know what? We don't have to. We can just do this. I don't know why I'm making this so complicated. Yeah, we just want to sequence through this pattern. Yeah, this infinitely. Right, and maybe we can do a random wait here. Just maybe it'll be short. Maybe it'll be long, but we're just going to do it once. And I want it to be a little more resonant. Yeah. And you can do all sorts of fun things by, like, you know, getting it out of phase. You know, I think if we do a function here and say like you know, maybe 7, maybe 8, maybe 9, choose. Yeah. So it's kind of drifting out of phase. You know, it's basically, if it does 8 of these, it's not going to be quite done when these are done. So when the duration and low-pass filters start back again, this one still has a couple of downward transpositions to finish. Okay, so this is like marginally more musically interesting than my sawtooth thing. Anyway, we're over time here, so this is I recognize this is like a lot to digest all at once. With you know, we have our various value patterns, which, you know, kind of a new language to chew your way through, and then we have events, and then suddenly this huge event infrastructure behind the scenes, which tries to take care of a lot of the details for you and lets you substitute in your own values at will. And then where's all my Pbind stuff? Yeah. And then when we have our own synth defs and loading on our buffers and whatever we want to do, then suddenly we have Pbind, which allows us to define sequences of events and then play them on a clock optionally, quantizing them as we saw last week. And, you know, this unlocks a you know, a sort of new world of sound sequencing options, allowing you to make what I think can be really complex and nuanced sequences, you know, with just a couple of Pbinds, which take care of a lot of the dirty work kind of behind the scenes. But you know, it's there are pros and cons, but I think it's a really important part of SuperCollider to learn. And if you get comfortable with it, I think it, you know, you've sort of like leveled up a little bit. Right? So, all right. Well, I won't keep you. As a reminder, the midterm should now be available, and it's 5 questions. I'll tell you right now, it doesn't deal with clocks, doesn't deal with quantization, doesn't deal with buffers. So you won't have to know everything, but you will have to, you know, be comfortable to a certain point with everything. So I will see you next week.
So the midterm is until tomorrow, 3 p.m.
Midterm is due, yeah, 23 hours from now.
3 hours.
Yeah.
Perfect. Thank you.
All right.